around the topic of this project MIPRE. So this MIPRE, this RFCS, titled Advanced Metallurgical and Micromechanical Modeling to Deploy the Microstructural Tailoring Potential of Press Hardening. Basically, we're going to talk about modeling and about press hardening, about microstructural tailoring in press hardening. So I will be the first speaker today. So I am Jaume Pujante from Eurecat. I'm a researcher here at Eurecat since 2010. I'm now the head of the research line on new processes for advanced materials. I'm an industrial engineer and a doctor in material science and engineering, and I've been working here since 2010, more or less, working basically in press hardening related topics and in high temperature processes, let's say. And yeah, today my talk will not be exactly about MIPRE, about this RFCS, although it is a little bit related. We'll talk a little bit about this project MIPRE and also about an internal project that's called SMART, and about activities related to Industry 4.0 concepts applied to press hardening. 4.0 doesn't sound so 4.0 anymore, does it? So it sounds a little bit old, a little bit boomer, but okay, let's keep this title. So yeah, let's move forward. First of all, I don't know if everyone knows what is press hardening. I will just explain it just a little fast, but I know that everyone more or less knows the topic. So press hardening is basically a sheet metal forming process where we form at high temperature. So it's also called hot stamping because it's stamping but hot. And we take a sheet metal pad and we put it in a furnace. Once it is austenitized, we transfer it to a cooled tool, so a cooled die, and it is pressed hardened into shape. So it's basically given the shape and given the heat treatment in one single step. This is what we see here, so an image that I've stolen from the internet. And the idea of press hardening is that it allows us to circumvent the banana plot. So we have talked a lot about the banana plot today, this morning, basically in the ToughSteel project. But we know that the higher we go in mechanical properties, the lower the formability of our alloys. Now, if we want to have complex shape and high mechanical properties, one way to do that is by press hardening. So we take a material that's nothing to write home about, so some ferrite perlite structure. Then we can heat it, and then we can form it while it is in austenite form. And in this single step, we can give it the shape, and it will be easy because it is hot austenite, and we can give it the heat treatment, and it should be easy too. Now, once we have centered the topic, we're talking about process, temperature, and quality in press hardening. And one of the things that press hardening involves is that we are giving shape when we are hot. And not only we are hot, we are in austenite state. So in FCC, it is easy to deform and it is easy to give shape. And temperature here is an important factor. So we have here some FLD. You all know what an FLD is better than I do, so I will not go into explaining that. But we can see the effect of temperatures here from a paper that we have found, 800 degrees, 600 degrees. The formability is very much affected by temperature. And this is one issue that could affect process, temperature, and quality. But this is not what we are going to talk today about. What we are going to talk about is about the quenching step and about the cooling step, because we think that the other one is a hygiene condition. If the sheet arrives at the press at the right temperature, everything should be formed at the right temperature. But what happens with the heat treatment? And this is what I want to talk about. This is a normal CCT for a press hardening steel, so for the 22 manganese boron 5. If we do the normal cooling, so the OK cooling, we would find a line more or less like the blue one that you see here on the board. So this will result in a martensitic structure. And this all makes sense, and this is what all we imagine when we are talking about press hardening. Now, when we talk about press hardening in a not OK condition or something strange happens, what our mind goes to is a thing like this green line. So you see this is very slow, and we cool it down very slow, and we end up having some perlite and some ferrite and things. Now, this is what we have in mind, but this is not something that happens by accident. If you see, I have not put it in red, and I haven't written accident here. I have put in soft zone, and I put it in green, because it is another condition. It is a condition that is actually not a condition that happens naturally. Let's look at the times. I mean, you see, here we are crossing 600 degrees at 20 seconds, 30 seconds. This is not a natural process. This is something that we have to force. Actually, if we mind the process window and the time where we are cooling the die, it looks more or less like this. It can be a little bit longer, but we'll move in this range. And if you see, this kind of cooling is something that does just not happen in the process unless we force it or we do things very wrong. If we think about a process where the die has bad contact or we have a hot spot, it will look more like this. So if you see the window of time, we are getting 500 degrees for 110 seconds. This is more like what a not okay process would look like. And this is usually a production problem, actually. We have a hot spot, we have some wear, we have a point where the die does not contact the sheet metal. So we have leveled the production problem, and we'll not talk about this. I mean, we are thinking about what if we do things right. And if we do things right, there are still things that can go amiss. And this is here where we can have a phenomenon of that we will call self-tempering. So basically, just imagine that we are cooling our piece okay, we are following a good path, but we open the die and we take the component out before we have reached temperatures that are close to 100 degrees to 100 degrees. And this is definitely something that can happen. And this will lead to something called self-tempering. And please, this is a gross oversimplification, and when Carlos speaks afterwards about MIPRE, we will see that there is much more nuances into that. But basically what we can see is that if we open the die with a piece that is too hot, the transformations will somehow interrupt, and we can have self-tempering. So this martensite that we are forming will be tempered martensite. So let's talk about this. Self-tempering, basic test. What we did in this paper that we published a couple of years ago, we wanted to study a little bit rudimentary what is self-tempering and how can it affect the final mechanical properties of a hot stamped component. And what we did is that we took a dilatometer and we started forcing cycle times that would look something like a self-tempering, this case. So, we have a die that opens before time, and we have a component that exits the die too hot, 400, 300, 200, 150 degrees, something like that. And what we did is that we took these temperature cycles where we would interrupt the quench and then cool slower, 5 degrees per second, 10 degrees per second, which is more or less air cooling. And once we do that, the results, okay, you will not surprise anyone of you, but of course, if we interrupt the quench at high temperatures, what we get is less hardness. And we get a microstructure that is no longer so martensite, fully martensite, or martensite with a little bit of bainite, but rather we have some tempered martensite, some tempered bainite, some even Stenger phases in there. And this is something that in retrospect it makes sense, and this is something that we could actually expect, but okay, it was nice checking that. And actually, what I said before, so this is the scenario that we're usually finding us when we have a production problem in an industrial process. It is not the super soft parts, no. It is usually this one. Afterwards, we went to a semi-industrial environment, and what we wanted to do here is to, okay, we took some thermal cameras, some pyrometers, we put them all around our press, and the idea was to measure temperatures to see if somehow we could monitor the heat treatment using this very simple equipment. If we see, we could measure more or less the sheet temperature once the die opened, and when it closed, then we can see, when we open the die, we see a plateau with the sheet that's a little bit hotter, and then we take the die, the sheet out, and when we see the temperature of the die, it's a little bit complicated. Basically, what we're seeing is the temperature of the sheet metal when we exit, and then the temperature of the die. And with all of this, what we did is that we did a campaign of tests, and we analyzed this using simple methods and using also artificial intelligence, because it was a collaboration with the group of artificial intelligence in Eurecat, and we wanted to start doing something. And the results are here. Look, this is the cooling rate. This is the harness. And what we're seeing, of course, there's a little bit of cheating here, because you see it's 1 second closed die, 3 second closed die, but what we're seeing is that the important parameter here is not the cooling rate. This 30 degrees per second that we say, okay, this is the sacred line that we need to cross, okay, but this is 400 degrees per second, this is 200, and we are still having harnesses that are below what we would expect. And this is because we are opening the die with a final temperature, so when we open the die, the temperature of the sheet metal is hotter than we would want. In retrospect, it makes sense. But the thing is that we could do these experiments. We saw definitely that self-tempering was an issue. And also, this little thing here, using some machine learning algorithms, we could also analyze these results. And these results are easy to analyze for a human. I mean, it's not a lot of points. But the machine arrived at the same conclusions that we did. And, okay, this is a good start. So we see that, okay, I will have to interrupt myself, but this, please keep in mind that these sensors that we used are nothing special. They are nothing exotic. So they are just pyrometers, thermal camera. Actually, in MIPRE, partner gas stamp is doing more or less the same. And it is easy and it can survive an industrial environment. All of this, with these very simple measurements, we see that in absence of production problems, we can still have self-tempering, and this is something that we need to take into account. Then, this self-tempering can be detected with relatively non-invasive measurements, so using simple equipment. And also, an AI-based analysis can be used to monitor this self-tempering and to have an idea of what is happening. And this is interesting, and this is where we wanted to keep studying. 10 minutes? Okay, it will be fine. So, the next step would be, okay, we have started to work a little bit with artificial intelligence in this application, and this application actually is a good one for artificial intelligence because we have a lot of things to control. Is it possible, I ask here, and of course, if I ask it, it's because the answer needs to be yes or maybe. Is it possible to devise a control system to prevent the effect of self-tempering on part quality? And this would be interesting, and this would be something worth studying. The agent would look something like this. So we have an environment, an industrial process. We can get some signals, put it into an agent, whatever it is an agent. It is a program, it is an algorithm, it is whatever. And then it will give us some parameters that it will input into the industrial process so that the industrial process is controlled. Why dynamic optimization in industrial environment? This is dynamic optimization. See, so we don't have an industrial process that is just with parameters 10 seconds, 15 degrees, and everything works the same the whole day, but rather it's something that gets changing, and that's changing dynamically because this agent is controlling the process and saying, okay, let's correct this, let's correct that. This is a dynamic industrial environment. This is not easy. This is non-trivial, but it gives some advantages, so it is worth pursuing. The thing is that this loop needs to be done at something similar or close to real time, and this is where the problem begins. This agent cannot make a simulation and 5 minutes later or 10 minutes later or 30 minutes later give a result. Okay, so this agent would look something like this. So we have an press hardening line, and we have some input parameters and some material, and then we have a result. Then from this result and from the process, we can take signals and feed them to an agent. This agent will analyze all of these results, and they will give us some parameters that we will input back into the project in the next cycle so that everything goes fine and everything is well. Now, the thing with playing with a system like this is that, of course, this is expensive and this is risky. We cannot just hook an industrial process into a machine and hope for the best and say, okay, here, learn. So we need to do it in a more controlled manner, in a manner that they're experimenting, because the point of all of this is experimenting and forcing parameters that are okay and not okay. This is where we have one of the tools in our disposal, and it is finite element modeling, simulation. A simulation is a good place to experiment because we don't break anything. So we can simulate a process, and then we can see how it responds. And with these results, we can go back to the agent, and the agent will give us conclusions. See, the agent doesn't know if it is a real system or not. It doesn't know if it is counting degrees Celsius or potatoes. It just doesn't matter. It's an algorithm that will just learn how a system functions, so we can feed it with a simulation. And this is more or less what would be a real-time digital twin, for instance. So this is a manufacturing simulation-based environment. Very nice word that I did not invent. I just copied it from another presentation from someone who was more clever than I was. But it has some benefits. So we have simulation as the main source of data and knowledge, so not the physical environment. And this is cheaper, and this is very much less risky. So we can explore configurations, we can explore scenarios, we can explore parameters. And this is very interesting. Now, it also has drawbacks, and even though it is easier than an industrial environment, a simulation is still long, and it is still costly in computational time and expensive at the end of the day. A simulation of a press hardening component like this one, the people who work with press hardening or with simulation, you know that it can take several hours, simulation like this one. So we need something a little bit faster, something a little bit more lightweight. And here is where we enter the next interesting concept. So I am just breaking down a little bit. I hope that we can all follow more or less the train of thought. And it is a surrogate model. What is a surrogate model? It is another agent, but this agent, what we'll do is that it will work instead of the simulation. So we will take the simulation and we will use simulations to train an agent. The agent, what we'll do is we put parameters into the agent, and instead of simulating, the agent can more or less approximate the result of the simulation. Everyone's following? Yeah. So we have an agent that we can train to simulate without simulating. Just by intuition, and artificial intelligence will learn to more or less, okay, this will give this result in a simulation. And this is super interesting, and this is, again, the same that we had before. So what is what we want to simulate? And here we go back to the beginning. We were talking about self-tempering. So here we are ignoring the forming part, and we are only thinking in the thermal cycle. This is a thermal cycle in a press hardening part, a press hardening tool. And you see that we have these peaks of temperature and then cooling, peak of temperature, cooling, peak of temperature, cooling, and more or less everything enters a steady state. This has been done through simulations, and it has been set up by a human. What we want to do is that maybe an agent can also approximate this temperature profile and can know, depending on the temperature of the sheet, depending on the die closing time, can approximate the temperature at the end of the cycle. And this would be very good because it would give the same result as a simulation without simulating. And this is what we started doing. So we simulated this environment here. It was just a flat die. We simplified a lot, and we went just to a flat die and a flat die press hardening. What we wanted to see is how the die heats and which temperature does the sheet metal have at the end of the cycle. So you can see more or less here. So we enter the sheet metal, it cools, and then it opens, and it goes out. And this is what we published in this paper here, so from Albert Avio, which is the guy who actually did the work. I was only there, so giving a little bit of support in the environment. And it was really nice work that I cannot technically explain, but I can give you the gist of it. The thing is that we ended up training an algorithm, an agent, that could give us the same answer than the simulation gave us, but much faster and much cheaper. How much faster? Okay, let's look at that. This is a window, this is just a small Python program where they implemented their agent. The simulation, it is easy because it's just a flat die. So more or less the simulation took 2 minutes, let's say, in giving us a result. We'll see now how the agent works, if everything works. So here what we're giving is a closing die time and then an initial temperature of the sheet. And it will give us the final temperature of the die and the final temperature of the sheet. Another value. Of course, here is a human just inputting the data, but you can imagine this hooked into a system that just inputs the values that it is reading in a line. And as you can see, it is almost real time. Maybe it is not real time for super fast forging of small components, but for press hardening is perfectly real time. I mean, the cycle time in press hardening is 15 seconds, and this is taking, what, 1 second to calculate? So we have an agent that can actually do the same work that we were doing in a simulation, but 2 orders of magnitude faster and much, much cheaper. Of course, it is more limited, but hey, it is giving us something already. So it is possible to generate a lightweight machine learning-based agent to act as a surrogate model of a finite element modeling scenario. And this model is limited, but it is much, much faster and much less computationally expensive. And please keep in mind that we have trained this agent with a simulation, but we could have trained this agent with anything else. It doesn't know if it is a simulation or a real environment. It only sees values. It doesn't know if these are degrees Celsius or if these are potatoes, again. So this is the power of what we're seeing, and this is actually quite impressive if you think about that, at least for me. So we have an industrial environment, and we are feeding everything to an agent, and this agent is taking decisions. This is what we wanted to do. We said, okay, we'll do it with a simulation, but the simulation is too slow and it's too expensive. Okay, we'll do it with an agent. And now we are at this point. This agent can't make a lot of simulations very fast. They are not simulations, but they are almost as good as simulations. And we can use this to train this agent. And this is the next step. So we have one agent that we will use to train a second agent. This agent is the surrogate model, and the other is the control system. This is another paper from Nuria Nievas, also a very nice work. And in this case, what we were doing is the same. So we were now playing to propose a control system that can say, okay, I want the sheets to be at, I want every component that I press harden to be no higher than 160 degrees. And what we will do is that we will change the cycle time. So we will change the close die time to make sure that all the components are okay. And how we do that? So this is more or less how it would work. So it will take into account the previous time, some signals, and then it will decide how many seconds the die needs to be closed to end at an acceptable temperature. And in this training, what we do is that it will just try parameters. And when everything goes well, we will give it a reward. And when everything goes bad, we will give it an anti-reward, so let's say. We will punish it. Punishing is not a nice word, but in the end we're punishing it. Don't worry, it doesn't suffer yet. So just so that you can see how the training goes, look how many iterations it had to go. 500,000 iterations, huh? And this is the rewards. So at the beginning, everything was punishment. Punishment, some rewards, and it goes better. What it means is that with the time and following the iterations, it is learning. At the beginning, it did very badly. But in the end, it did very well. We are not punishing it anymore. We are rewarding. So it shows that here it has learned, and here it was already learning. Okay? But look at the amount of iterations. This is the reason why we had this surrogate model. It's much faster than simulation. Otherwise, we would have done 500,000 cycles. And this is more or less how the best solution in the end worked. So for the first cycle, it kept the close die time close. The dice were accumulating heat. And once the dice were too hot, he said, OK, let's make it a little bit longer, and let's stay within this time. And this is more or less what humans do when we take simulations and we say, OK, in this line, we will put 25 seconds or 18 seconds cycle time. But this is being done by a machine completely autonomously. This is interesting, and this is a powerful result. OK, so let's get to the end, because I'm already over time, but I'm my own moderator, so I will allow it. We had an industrial system that we wanted to control with an agent. We said, OK, this is too risky. Let's put a simulation, and we put a simulation model to train an agent. And we said, OK, the simulation is too expensive, and we took this surrogate model to train the agent. But now the agent is trained. What would happen if we put this agent to work on a real line? A real line is a real physical system. And we went back to our physical system, and we started doing some trials. And what we did, it was something to behold. Because we were taking sheets from the furnace. So every 30 seconds, we took a sheet from the furnace. We put into the die, and then we noted the temperature at the beginning, the temperature of the dice. We input everything onto this control system, and this control system proposes us how many seconds the dice need to be closed for the temperature not to reach the uncontrolled, the threshold level of 160 degrees. As you can see, the signals are not as nice as we had at the beginning. And also here you can see a frequency distribution of the temperatures, initial temperatures, and the transfer time, and so on. When we were simulating, everything was very closed and very well controlled. Here, because the simulation was very, very simplified, here we have a lot of noise. So when we went to the actual system, it looks like this. So this is what the simulation would have said is the final temperature. Here is what the agent said would be the final temperature, and here's the real system. What is teaching us? What is here showing us? OK, the agent didn't do super, super well, but actually the agent was trained with the simulation. And the agent is just trailing the simulation perfectly. If we had trained it with the real system, probably we would have something closer to a real system. Or if the simulation was more complex and including more complexity from the real system, it would follow that. Next work onto that, this can be improved, and we are definitely working on that. I'm not allowed to explain a lot of things, but there is ways to improve this kind of approximations, and these ways are interesting. So, time for the conclusions. In absence of production problems, we said that self-tempering is an issue and is something that appears, and it's basically depending on which temperature does the component end the production cycle. We saw that we can make simulations, but we can also approximate these simulations via surrogate models. And these surrogate models are more simple, they need to be trained, but once they are trained, they work almost as well as the simulation and much, much, much faster, a couple of orders of magnitude faster. And then we can also use this same kind of models and machine learning-based agents to control the system, to approximate the end result. And this is everything from my side. So thanks a lot for your attention. I hope it was interesting for you. This was related to this MIPRE project, but also to this internal project that is SMART. And if you are interested in this kind of things, you can drop us an email or something like that. But also, you can check these papers. They are super interesting and super nice to look at. Thanks a lot. OK, so this was my presentation. Questions will be later, but now we have Carlos Capdevila here, who will talk about the MIPRE project. Carlos Capdevila is a PhD in physical science and researcher at the National Center for Metallurgical Research, so CENIM, of the CSIC, where he currently holds the position of director. Carlos is part of the solid-state transformation group, Materialia, where he's involved in research on the development of heat-resistant steels for applications in power generation systems under extreme conditions. Recently, he also participates in an ambitious project within the framework of Industry 4.0 to investigate additive manufacturing and the role this disruptive technology can have on the social and industrial environment. So likewise, driven by the urgent need of the steel industry to reduce its carbon footprint, it says it's also involved in the Innovative Heroes project within the framework of the Next Generation Funds, where the potential of hydrogen in steel production is investigated. And Carlos will have a little presentation for us, talking about this project MIPRE and explaining us a little bit of the results. So Carlos, thanks a lot.
So thank you, Jaume. Thanks all for attending. Jaume, you speak very fast. Actually, I am not reaching your speed at all. So I am not trying to, because I am going to be blah, blah, blah. That way anyway. So thank you for the, my role here is try to, well, introduce the MIPRE project to everybody. And is quite linked with the previous talk, and is broader in the sense that we want to combine modeling plus characterization of those type of microstructure for the press hardening process. So first of all, so I would like to thanks to the partners of MIPRE. We are in Spain. We have CENIM in Madrid and Eurecat here, and Gestamp Abrera plant here in Manresa. France, we have ArcelorMittal producing the steels, and also Institut Jean Lamour, which is characterizing and modeling the phase transformations that they are involved. And finally, Luleå University in Sweden, which is also part of Gestamp team, is working in Sweden. And Luleå is in charge of the mechanical testing of high-speed mechanical tests mainly. And regarding my team in CENIM, so I would like to thank you to Vicente, which is sitting over there. He's holding the column, actually, so it's a good thing. And Francisca Garcia Caballero, which is leading the research team in CENIM. So, the focus of the MIPRE project was focusing on the press hardening, because we believe at the beginning of the project that we still believe in, that the press hardening offer a good dimension control of the parts that we want to produce, but also offer the possibility of tailoring design of different parts with different components. And that was one of the, the topics that we want to think about it in this project, but also the combining with the boron steels, because boron steels is very well known for everybody. Has been in use for a long time. But there is still room for new development, and to develop something new with a product we have been using for a long time, you need to know very well what's exactly working in the process. For this reason, the aim that we want to go with this project is basically try to, for the sake of knowledge, of course, but also for application, to integrate the different phase transformations models and to predict engineering properties in this type of process and materials. So the goals for MIPRE is summarized in that way. So from academia part, we want to improve all the microstructural models that we have so far to apply to this process. So basically, there are the Bainitic transformation model and martensitic plus tempering and precipitation modeling. And this is for to create a knowledge-based model approach, but combining also with another one, machine learning supported process of the industry ecosystem, the Industry 4.0 or 5.0. If we started the project with 4.0, we are going to finish the project with Industry 5.0, and but the ecosystem is basically the same. And we want to combine both in order to have a footprint, digital footprint of the whole process. That was the goals. Different thing is the thing that we achieve actually on the project. But linking with the presentation of Jaume, The machine learning predicting part quality was developed in Gestamp in one of the industrial, of the press hardening tools that they have in a plant, and they were censoring the tool in order to to find out exactly which are all the parameters values during the process. And the idea was to correlate those values with when you have find out something wrong during the process, try to correlate what was wrong with the values that they lead to this wrong part of the process. And in that way to build a database of possible failures that you are going to obtain with the processing during the production of a certain component. And other parts, as I mentioned before, we were dealing with Bainitic transformation models, but also with the martensite and the temper martensite modeling. Here I put the results that we achieved with the Bainitic transformation model. This work was mainly done in the Institut Jean Lamour in Lorraine, in France. And they actually got nice results because it's a model that actually can consider the effect of the austenite grain size that we are going to have in the model. So this type of transformation, which is this passive transformation, is quite complicated in order to introduce this type of effects. The solid lines are the lines predicted by the model. The dashed lines are the actual experimental values that we obtain in the project. Of course, there is room for improvement, but the direction is quite good. So we also introduced the martensite transformation and the temper martensite transformation model in order to implement, it's going here, in order to implement in a complex composite model, introduce the effect of the microstructure for the final mechanical properties that we are going to have in terms of tensile properties. So from as an input basic experiment or basic microstructural parameters, we can get more or less, or we can get a result for the tensile or strength properties of the steel. So these are the work that we are currently done because the idea actually is once we have these knowledge-based models, how to introduce those in a finite elements model that they can implement the forming process quite easily. And of course, these smart objectives that they call in the project. So we have to supply that, and also to supply the numerical toolbox for the producing parts in the press hardening, and also generate a component actually when the results of the model implemented for processing and get the final parts. We are actually in this stage of the project. But let me, once I summarize basically which are the aims that we want to, or we were seeking in that project, let me just highlight some of the interesting results that we got from my side. From my side is the microstructural characterization of the materials that we are using in the press hardening. So we were working with industrial heats, which is a PHS 1500 steel, which is very well known. But also we introduced some variations in the silicon and aluminum content in order to see how is the role of the retained austenite microstructure in the microstructure and also in the mechanical behavior. And we were taking into account the different parameters that we have in the press hardening, so the reheating temperature, the contact pressure that we have in during the process, the tools temperature, and the die closure time that we are going to have. And we obtain, or we select 10 different conditions, combining both or the 4 different parameters that we are going to to analyze. We explain here basically where are the samples obtained from the different tensile test samples produced after the processing. And we got some results here. The legend on the right hand side, is over here. The size of the circles, it depends on the type of composition that we are going to use. And then the colors, blue or red, it means that the die closing times that we are going to have. So basically, there is a effect on the increasing with the temperature of the tool temperature on the strength, which is decreasing the strength, is also having some variations with the elongation. All of these results, I forgot to mention, are corresponding to the industrial steel, the PHS 1500. And we analyze and we observe how the strain to failure, for example, and the bending angle is improving with a shorter time for closure. With these mechanical results having in mind, so let me give you a rapid guide of the different type of microstructures that we are going to face. So this, in these graphics, we have, when we are calling bainite, so we are calling bainite is something quite broad because there are different type of bainites here. And they are behaving in a very completely different way. So we call granular bainite when you have this shape, upper bainite. So there are carbides here and ferritic glass over there. When there are no carbides, but there are retained austenite, they call carbide-free bainitic microstructure. And lower bainite is when the precipitates are inside the ferrite. And when you have tempered martensite, you also have precipitates inside the ferrite, but they don't have a preferential orientation with the microstructure. So these are the microstructures that you can obtain during the process of pre-hardening, and you have the different type of microstructures. You can see the difference between the ones that I mentioned before. And of course, you characterize the amount of the different type of microstructures for each of these conditions, and determine the retained austenite. So having in mind here, these points correspond to the 1500 steel, the experimental steel, which is no silicon, and therefore there is no retained austenite in the microstructure. So it's, which is good to analyze the effect of the lath-like microstructure without the role of retained austenite inside the microstructure, because if you observed in the previous slide when I mentioned the difference in the scheme, you have, when you have two phases, all the results can be distorted by the presence of the second phase, which is very difficult to control. So when you avoid this second phase, it's easier to control the microstructure. So here, for example, are the microstructure obtained at the different tool temperatures that we obtain. From room temperature to 400 degrees C. In a quick view, could be similar, but there are not similar when you are going to the deeper inside and you observe in the mechanical behavior. And I would like to focus here on these conditions, which is the 400 degrees C, 30 seconds closure time, that we have a combination of lower bainite and tempered martensite. And this is the green area that I put here in the samples with the different, the tooling temperature is here, and the different mechanical behavior. And you can see the role of the closure times, for example, with different values of properties. And there are, as I mentioned, apparently there are no differences when you have 10 seconds or 30 seconds. But when you are going inside, you can see how is the precipitate distributed inside the microstructure. So when you have these precipitates over here, or I put these red lines to highlight how they are oriented. You have a lower bainite microstructure. When you have those that they are, a random orientation, you have a tempered martensite. And then combining both, is, well, could be is something that is, as Jaume mentioned before, when you are cooling or you are processing your material and you have the PHS 1500 degrees C CCT, you are exactly moving in this area, then you have bainite and you have martensite. So depends on the time that you are going to stay during the processing, you will have more bainite and more martensite. So this could be at the beginning a disadvantage because you are not able to reproduce exactly the same microstructure, but if you are able to control that, so then you will control the properties. The process is just controlling the closing time during the press hardening. And this is basically the conclusion that I will draw from this talk. I don't want to just only to highlight some part of the project, but basically regarding the whole project, so there is a two-fold modeling approach that we use in MIPRE, from an academic approach and machine learning and combining both. An integration on fundamental solid-solid phase transformation models. We want to generate an ICME computational model to describe the press hardening. And regarding this, the role of the microstructure, so replacing tempered martensite partially by lower bainites looks to improve the boron steels without losing significant strength. And discrimination and quantifying tempered martensite and lower bainite is very difficult. And we still need to do a lot of work just to find out a quick method to do that. But thank you very much for your attention and open for questions.
Thanks a lot, Carlos. Okay. You want to come?
Yeah.
Look, we can do something like this. Take the other one, and then you can take the microphone for you. Okay, thanks a lot. So, the floor is open for questions, if you have any.
Jaume talks so fast, but you give a lot of information in some slides as well. So, now maybe the last sentence is really relevant. We have to differentiate low bainite demand is super difficult. Yeah. I know that we don't know how to do it now, but any idea of how we can, in a practical way?
No.
Yeah.
Unfortunately not. We have been rambling around with EBSD for a long time, so long years, trying to find out this technique as a tool, but actually it's very difficult, and especially in this type of microstructures, which is quite fine. And there are fundamental effects on the EBSD for when you have the presence of a second phase that even can give you wrong results because they are overlapping peaks, and something like that is complicated. I don't know, maybe we try in a previous project, actually it was a project with the coordinator was Silvia over there a few years ago. We tried hard, and in my opinion was the best approach that we got. Is basically taking model alloys, then you are sure that you have a microstructure, and then train the machine to say, okay, when you have this pattern, is this microstructure. And then when you have other pattern, this is the other microstructure. And try to combine. This is going to work as long as you have the same carbon content. But it's not universal. And that is the problem.
At least it's a good basis for understanding properties that really, really small microstructural arrangement has a significant effect. So
yes, that's the... Yeah, well, the honest result from the project is we cannot predict at all the microstructure that we are going to have. So we have to survive with the microstructure that we have. The only thing that we are happy is we know exactly the microstructure that we are going to have, and we can, in certain level, control. That was something that we didn't before the project.
It's not a miracle or a magic. We know what happens, and try to go for that.
That's the idea, and maybe this is a good step because we playing with the closer time. We can improve the better and also control the tailoring the properties in the part. Yes.
Interesting. Thank you.
Thank you.
In this regard, just following what you said, so basically what the kind of concepts that we have developed here could work in production of steel, so for designing of, even if it's cold rolled steel with heat treatment and so on? The microstructural transformations?
Well, the problem is, yes, but I think that with the cold roll steels, maybe the recovery and can also play a role, and here we didn't have that effect. But the basics are the same.
Okay.
Yes.
Interesting.
It's just question of adjustments, I think. That is true.
Okay, thanks. Any more questions? Online? I will have a last one. And then
Which is not arranged, by the way.
Which is not arranged, by the way. And it is that, okay, we have seen results for 0.2% carbon, but the trend in the market is going to higher carbon. So using over 2000s, we have seen a couple of them.
Yeah, it's true. We have been testing also 0.3 steels, and the tendency is the same. I didn't show here because it's for consistency with the composition of we have industrial and laboratory heats. And laboratory heats that we perform with 0.2. So in order not to introduce the effect of carbons that we could change everything, so we didn't show the results of 0.3, but we have been working with that, and we can say that the tendency is the same.
Okay.
Yeah.
Thanks a lot. So please, let's thank the speaker, and
thank you.
We can call this session over. So Dr. Dani Casellas, our scientific director, will just provide some closing remarks.
Yeah, we will distribute the test of all of you if you can. No, that's okay. No, it was the end of a really nice, interesting, colorful workshop with we touched different aspects related to steel, to high performance, toughness, the risk of hydrogen embrittlement, and now more the details of microstructure and properties. I think it was really interesting to see how the steel world is moving. We always say here we have one representative from our steel sector, some others online, of course, but we like to say, as we generally say, is that steel is still alive, and I think it's really that the coming times will be also excellent for the steel sector and also for the material scientists, because we see a lot of challenges to address. Nothing else from my side, just to give all the acknowledgement to all the participants. Thank you all for the participation, for the questions, for the interest, for the interesting networking we did during the coffee break and during the lunchtime. We will distribute in the coming days the presentations of the speakers, so you will have material available to enjoy again what we showed today. Please don't hesitate to contact all of us. You have our contacts. In the presentation you have the emails of the presenters. At the end, networking, I think, is the most funny way of working that we have. We like to improve our network of colleagues and collaborators. Nothing else, just to say bye-bye to those of you online. The ones that stay here, if you want to join for a visit at the Eurecat Labs, just meet 5 minutes here in the hall. Thank you all. I hope you have enjoyed the workshop and have a nice week. Thank you.
Thank you.